system engineering engine and its associated processes, identify the attributes of system engineering. Unit 1.1, common definitions of systems engineering. Today we're going to talk about system engineering, what it is, what does a system engineer do when they come to work every day, and specifically, how does it apply to the missions that NASA does in the aerospace community. So a lot of the other material you're going to see in the course going forward, we'll get into the specific processes, the tools that are used by system engineers in their daily life. But today we're going to kind of back up and just talk in general, what is system engineering all about? A system is an integrated composite of people, and people in a lot of cases in system engineering, you're talking about all your discipline engineers. You have thermal engineers and power engineers and a whole variety of people that are involved in a system. You can't forget, sometimes people think of system as the product, which you see on the slide as well. The product is the actual physical hardware and software that you're going to develop as part of the system, but the people are just as important to developing a system engineering concept. So people and products, and then you see processes on this slide as well. So all three of these are kind of key to putting together a system engineering process and to managing a system development activity. So all of these are combined to satisfy some need or goal or objective that you set out for the system. So we'll talk more about that, but the goal is to kind of set a sight where you want to get. What does this system need to look like? How's it going to operate? And then what are the people, products, and processes I need to put in place to make all of that happen? The term system engineering really was developed in the 1940s. So there was people doing system engineering forever, right? Anytime there was a big project, when the Egyptians built pyramids, they had to have some processes, they had to have some way to communicate because the system was too big for any one or two people to be able to kind of manipulate the whole thing and make it work. So when you have these big teams, you need to have standard processes and tools. So system engineering has been around a long time, but the formalizing of it really developed in the US in the 1940s, so kind of in the World War II era. And the Nike missile program in the 1940s was kind of the first program where people started to use the term system engineering. The Nike missile program for the Army was a way to try to defend the country from jet aircraft that might attack. Jet aircraft were being developed, and the threat of jet aircraft couldn't be met by the traditional ground-to-air missiles that were available. So you needed high-speed, highly accurate missiles, and that was going to be a very complex program that involved a lot of different technologies coming together. And so the idea was it's a very hard problem to solve. You needed to bring together a team of engineers, and then you had to have engineers who could kind of make sure they were coordinated and that a system was developed out of it.
Realizing the importance of this anti-missile system to the protection of the free world, the Army is pursuing the development of Nike Zeus on a high priority basis.
When it comes to NASA's history, our first big effort in system engineering was Apollo. In the Apollo program, you were bringing together elements from around the country, and a lot of different systems and capabilities had to be brought together to make it work. And so system engineering at NASA really started to be formalized during the Apollo era. And at this point, and if you go online, there are many sources, the NASA System Engineering Handbook is available many different places online, where you can see all the different ways now that we have formalized that methodology. And that's again what you're going to be learning in this course. System engineering is a rigorous approach to designing, creating, and operating a system. And you know, there's other things too. You're trying to optimize the system to meet the requirements and the goals that you've set for it. Let's just talk about the two words. So first, this involves engineering. So system engineering at its core is engineering work. So engineering being the application of physics and math and science to solving some problem. There's something that needs to be done, and engineers step in and use the laws of physics and mathematics to go ahead and find some solution for it. And there's all kinds of different disciplines may be involved, right? So depending on the problem, there might be chemists involved, there might be metallurgists involved, but the end goal is to engineer a solution to some real world problem. And so there's a couple examples on that chart, something like building the Hubble Space Telescope mirror that you see on the one side, or on the other side, you see some folks down at Marshall Space Flight Center trying to build a new type of lunar lander. And so in either case, you've got a team of people coming together, and they're starting to look at the different ways to make this system work. Now, a lot of engineering can happen at the very basic level. So some engineers are only working on maybe the design of a battery for a spacecraft. Some engineers are only working on how to build the thermal coatings that go on the outside. those very specific engineers that are working in their disciplines, that engineering can happen at a small scale level with small teams, and they can make changes just based on their experiences and develop a better and new product based on their experiences. But when it comes to bigger things, not just maybe a small application, engineering can become more and more complex. So if you go to the next chart, you see that the next part of system engineering is the word system. And so as problems become more complex, the engineering techniques and the processes that you need to use also become more complex. The number of people involved becomes more complicated. Here you see an example of the space station. So the space station is an example of a large system. You see that there's one element of it is the space station itself, the thing that's in Earth orbit, that's allowing crew to be on board and running experiments and doing all kinds of cool and neat things. But that's only one part of the space station system. What you see on the rest of the chart is all of the other elements that make up the system. There are cargo vehicles delivering cargo to the station that are coming from all over the world, Japan and Europe, from commercial vendors, from the Russians. There's also crew vehicles coming back and forth, the Soyuz capsule delivering crew and returning them back to Earth. There's also a lot of other elements of this system. You see some large communication satellites in the background. Those have to be able to relay data from the space station down to Earth so that people can communicate with that crew on board. There's also many facilities spread out around the world that have to be integrated together to make the station operate, to send information up to the station, to take the data from the station and send it out to the scientific community that needs to see it. So in this case, you've got a very large system that has to be coordinated with thousands of people that have to make this thing work. And this is where system engineering comes into play. And so system engineering, it really adds a discipline when you get to these large scale projects. So as engineering has become more and more complicated over the years, the idea is mature that you need tools to do this. You need processes, and those processes need to be standardized so that everyone speaks the same language. Everyone uses terms that everyone else can understand. And so that's a lot of what you're going to learn in this course is what are those terms and what are those processes that everybody uses. The system engineering approach consists of identifying and quantifying system goals. And so at the beginning, we'll talk that you start with an abstract idea. You'd like to maybe learn more about the universe and how planets around other stars might be able to be seen from Earth. And so I've got this goal, I've got this very high level thing that I'd like to achieve. Now I have to break that down and understand how can I develop a system to actually do that. So kind of use an example here. You see some pictures on this slide that maybe remind you of the space shuttle in some way. Maybe not exactly what you remember the space shuttle looking like, but we're going to walk through this process. And at the beginning, you've got this high level goal that you'd like to achieve, and maybe you have many different ways of developing a system to meet that high-level goal. So, and it says the creation of alternative systems and design concepts. So along the way, as you're trying to meet this goal, you may try out a lot of different ways and a lot of different systems that might be able to achieve that goal. Now you want to go through a number of trade studies. So the system engineering approach consists of performing trade studies, design trades, where you're starting to look at, well, which one of these potential systems might be the best at meeting that goal? What's the optimal way of achieving what I'd like to achieve with the system? So the system engineering approach consists of selecting and implementing that best design. Best is maybe, some subjective, some objective. You have certain things like in the case of what you see here, this was actually some early design work for the shuttle. You have some best might be it has to be able to carry the most payload up into space if it's a space shuttle. But then best might be you think it's the safest way of doing it. So there might be some subjective and objective ways that you're going to consider what's the best way. And once you've selected an approach, you're going to go through and do some verification of that design. And we'll talk more about the term verification all the way. But verification says if I build that system, as I'm building it, I want to check to make sure that in the end, it's going to meet all of the requirements. Can it carry all that payload to space? Is that shuttle going to do all the things? Can it carry 7 crew members? Is it going to do all the things that I set out for it to do when I first wrote down my goals and my requirements up front in this process? And so as you go further into the process, you've verified that the system is developing the way you want it to meet that high-level set of goals. And then at the end, you're going to say, okay, I've got this vehicle, I've built it. Now, can it meet the goals that I set out for it at the beginning? So we're going to learn about a term called validation, where at the end, you want to know, will it operate the way I said it should when I set out to build this system. And so we'll learn about verification, where along the way you're seeing if it'll meet each individual requirement, such as how much mass can it take to orbit. And then we're going to validate the entire system to say, as a system, does it do all the things? Does it operate the way that we expected it to? We'll talk about one of the major processes of system engineering. It's kind of the largest abstraction of system engineering is, how do you move from an idea to a system that's completed and operating? And so here you see the Mars Curiosity rover. And we're going to use that as an example to kind of walk through very quickly to describe the process of system engineering. In the upper left-hand corner, you see the initial requirements that the scientific community came up with to come up with a new rover to send to Mars. They said, gee, we'd like to learn more about the geology of Mars, more about the atmosphere of Mars. And we'd also like to know if Mars could have had life on it at some point in the past. Was the environment conducive to having some form of microbial life develop and survive? And so when you're doing system engineering, you take those initial ideas, and now the first step is going to be to look to see if there are any tools out there that already can do what is needed to be done. So if you look in this case, there are other rovers that have gone to Mars. So could those rovers do the science that's being asked for? Could they answer the questions that you've come up with? And so there was the Sojourner rover, in the late 1990s, early 2000s. There was the Spirit and Opportunity rovers. So you can look at the science from those rovers and say, could they help us in answering these basic questions? The first step of system engineering is there some way to get this information